All right. Well, I know you guys can hear me because you've been responding to me. Can you see the old slideroos there? Cool. Okay, let's start off before we get into lecture set number 4 and we kind of pick up where we left off last class. I'll just give a few quick announcements. The first announcement is about assignment number 2. So maybe what I'll do is pull it up so that we can just take a look at it and everyone can contemplate what it is they have to do. So here is the second assignment. I posted this yesterday. It's due on February 11th. So that's the Friday. It'll be submitted in the same format as before. So it'll be handed in via CrowdMark. It'll be a more traditional CrowdMark setting in that there will be a different box for each of the questions. And it's due at the end of the day. So it's a combination of material from lecture sets 2, 3, and 4. So there are some questions regarding the deviance. I'll talk about that momentarily. And the Wald statistic, I'll also talk about that in a little bit as well. First question is kind of a couple quick short proofs. You can see that they're only 2 marks each. They're just proving certain properties of the expected value of the score function. Sorry, in part B, that should be the derivative. So I'll have to update that. I just noticed that right now, because otherwise that doesn't make any sense. So that should be the expected value of the derivative of the score, but I'll update and repost that one. So those are short proofs, and you can use the properties of the exponential family that we have established in class. So in lecture set 2, we wrote out expressions for the score function in terms of the components of the exponential family. So you're free to use you can use those as starting points. You don't need to rederive the score function or any of that. You can use what we have done in lecture. Question 2, similar idea. So this is a direct application of a distribution that belongs to the exponential family. So we have y, which is distributed Poisson with parameter lambda. And we want to use the properties of the exponential family to verify that the expected value equals the variance. Again, you are allowed to basically start from what we have already done in class. So in lecture, we wrote out the components of a Poisson distributed random variable. We showed, without giving too much away, like what AY is and what B theta is and this sort of thing. In this case, it would be B lambda, but it's the same thing. So you can start from that point and then just show that those 2 properties are true. This is going to require you to take a few derivatives, and then it's going to require you to fill out the appropriate formula. So that's why this is worth 6 marks, because there are, basically 6 different steps that it's going to take to finish this problem. Okay, question number 3. Question 3 is one that I spent quite a bit of time on setting up yesterday. I'm very proud of this question. It's not overly complicated, but I still like it. Okay, so we have y1 to yn, which is gamma distributed. So beta is known. The probability density function for y is given below. So make sure that you use this PDF. Otherwise, things aren't going to work out exactly as they should. So this question is basically lecture set 2 and 3. So I'm testing whether or not you understand how to write something in exponential family form, whether or not you understand what it means for the response variable to fit into a GLM framework. And then we're looking at a variety of topics related to deriving the log likelihood function and the score functions. You can see that in question 3 on part F, in part F, you're being asked to explain and show what the Newton-Raphson updates are going to look like for alpha, which is one of the parameters in this distribution. So this is a theoretical question, but you still have to derive the associated components of the Newton-Raphson update. And then in part G, you actually have to implement the Newton-Raphson in R. So there is a computational aspect to this assignment, which should be expected because that's going to be consistent throughout the semester. There's a hint there. So when you do take the derivative, when you set up the score function, you should end up with gamma prime of alpha over gamma alpha. This is the digamma function, and you can implement this directly in R using the digamma function, digamma. So there's a little hint just to tell you, or just so you know what function to use in that situation. And then after you finish G, so you implement the Newton-Raphson, you run it to convergence, then you can check your estimate using that data set. And this follows from what we had done in lab last week and discussed in lecture last week. Any questions so far? All right. Okay, question 4 is another model fitting problem. So we have data basically across the years 1984 to 1988 in quarters. So what I mean by that is you can see like we have quarter, year, and then for each year you have 4 measurements. So you can think of these as successive running across the table, right? So quarters 1 to 4 for 84, 1 to 4 through 85, 1 to 4 through 86, etc. So you can organize these from 1 to 20 and given their time point. So basically what we're doing here is we're trying to fit a model to this data. The suggested model has a Poisson distribution with log link function. And what your goal is to fit this model using the process that we discussed at the end of lecture set 4. So we went through an illustration of how we would do this using the identity function, and now we're trying to do it using the log link function. So you need to basically set up that W matrix and the Z matrix, and then use that to construct X transpose XW times beta and X transpose W times Z, and then use that to update beta. So we talked about this process last class at the end of lecture set number 4, or the end of lecture set number 3, sorry. And tomorrow in lab, we're going to go through the implementation of that process in R. So you will have examples of how to do it, but you're still going to need to redo essentially the derivatives and rebuild the W and the Z matrices. Okay, so that's again basically the same. It's a exercise based off what we did in lecture set number 3 at the end of lecture set number 3. And then the last question is a question about deviance in the Wald statistic. So we're going to talk about that in lecture set 4. Probably we'll get to that today, I would imagine. And these questions are basically just asking you to implement and interpret the deviance. You don't need to use a computer here. All of this can be done by hand, but you can do the calculations in R if you want. All right. Okay, so this is a more traditional assignment, sort of as I had mentioned before. We have like the report style assignment for assignment 1, given the topic. And now we're kind of getting into more traditional styles of assignments, asking pointed questions based off the topics we study in the course. Okay, and again, this is due February 11th. So that would be a week from next Friday. Yeah, so 2 weeks from this Friday. So there's still quite a bit of time to get this done. And you can start this today. And you could finish everything up to the end of question 4, and you might even be able to finish question 5 by the end of today. Tomorrow in lab, as I mentioned, we're going to go through an example of how to implement the model fitting process for the GLM in R. So we're going to use the data and the structure that we defined at the end of lecture set 3 and implement that in R. That's not going to take 2 hours, but whatever time it takes, hopefully around an hour, we'll spend discussing that topic and implementing it. And then at the end of lecture, or in the remaining time, we'll have a working session where you guys can get started on this assignment. Okay, so that's the first announcement regarding assignment 2. The second announcement is regarding the first term test. So we have 2 term tests in this class. They are on February 3rd and March 3rd, I believe. So they're a month apart. February 3rd is next Thursday. So our first term test is therefore next Thursday. That's going to be held online using Crowdmark, and it'll be run during the lecture hours. So you'll have from 11 until 12:20 next Thursday to complete the first term test. I've been, kind of thinking about how I want to run the test, what material I want to use on the test. I want to make it as fair as possible, given where we are in the course and what we studied. So I think what I'm going to do for the first term test is ask questions based off of lecture set number 1, which is the regression lecture set 2, which is the exponential family lecture set. And I think that will be all that I'm going to use for the first term test. So the first term test is really going to be about GLM framework, exponential family of distribution, and essentially review of regression analysis, which is kind of nice. So it's familiar in that you really only need to focus on studying exponential families of distributions, what it means to be a part of the exponential family, what it means to be in canonical form, how you can study properties of the exponential family based off of the derivations we have done in class. You'll have to understand the log likelihood, how to derive the square function, how to solve for MLEs, the role of the information function, all that sort of thing. So everything that we discussed in lecture set number 2, and you'll also have to understand what it means to fit in a GLM framework and what is appropriate for that kind of question. So in addition to that, I'll ask questions from linear regression analysis. So what I'll probably do is, ask some theoretical questions about, maybe the residual properties, maybe some discussion questions based off of the model fitting process for a linear regression model. And I might give some R output and ask for interpretation, or I might give you a fitted model and ask for interpretation of those values and ask about model assessment. Okay, so that's my plan for the first term test. Again, lecture sets 1 and 2. I don't want to ask too many questions beyond that at this point because you haven't had an assignment on it yet. So this first term test, I think, will be relatively easy to prepare for, and the material will be pretty familiar, given that I'm gonna ask regression questions, like linear regression questions. But that does mean that the second term test is going to be, in terms of material, is going to be more difficult because that'll include lecture set 3, 4, probably lecture set number 5, and maybe 6 as well, depending on where we are by the time March 3rd rolls around. So there will be more material, more new material on the second term test, essentially. All right, so again, that's going to be next Thursday from 11 to 12:20, administered through CrowdMark. So you have the hour and 20 minutes to complete the questions and upload your solutions. And then the second assignment will be due the week after that. So if you want, in terms of preparing for the first term test, one of the best things that you can do is start working on assignment number 2, in particular questions 1, 2, and the first half of part 3. Those are representative of the kind of questions you can expect on the test. Given that the test is online, it obviously will have to be open book. There's not much that I can do in the way of controlling for that, nor am I going to try. So, you can use the course materials on the test. I'll find questions that, you haven't seen before. And the best way to prepare is to essentially review what you have from Stat 378, because I'll be asking regression style questions. So model assessment, interpretation, discussion on variable selection, all the things that you went through on the first assignment, and studying the exercises that we did in lecture set number 2, the definitions from lecture set number 2, and starting on assignment number 2, particularly questions 1, 2, and the first half of part 3. Okay. Any questions? Okay. Easy peasy. All right. So I'll also send out a formal announcement about that after class and reminders leading up, just so that everyone's on the same page. Okay, so let's get back into lecture set number 4. So lecture set number 4 has a few different topics in it, as you might recall from last Thursday. I'll just quickly review the main points. So what we're working through right now are examples of how to derive the score function and then assess or derive the sampling distribution of said score function. We're going to extend this idea to MLEs after the first two examples. So we're almost done the example with the normal models. Then we're going to look at one in the binomial case. And then we're going to talk about assessing the sampling distribution of the maximum likelihood estimators directly. Following that, we're going to introduce the deviance measure. Or I'm going to introduce the deviance measure. We're going to discuss what it is, the formulation of it, and how to use it. This is one of the key model assessment tools for GLMs. And then we'll look at a few more illustrations of different hypothesis tests. In particular, we'll talk about a method for comparing subset models from the same exponential family and, well, subset models from the same exponential family. So in the same GLM framework. Okay, so we looked at a few properties of the score statistics last class. First, we redefined a few properties for our GLMs. So the expected value formula, variance formula, the definition of the link function, and the definition of the score function. The score function we drove in lecture set number 3, just as a reminder. Whereas the first two properties we drove in lecture set number 2, and the link function, that's just the definition of the GLM. All right. So we talked about how under certain conditions, we can assume that the isotopic sampling distribution for beta in this case is going to be normal. So we have the score function divided by the square root of the information is normally distributed. And then we have the score function squared divided by the information function is chi-square distributed. So if we know that the data from which we are sampling is normal, then these are exact distributions. Otherwise, given that our response variables are members of the exponential family, these are all approximate, but they're the conditions under which are the conditions that are required in order for these sampling distributions to be approximately normal or chi-squared are met. So we can assume that these are asymptotically normal or chi-squared. All right, so we left off looking at an example where we drove the score function and found the corresponding distribution of said score function. So we're working in the situation where our data is normally distributed. So we have y1 through yn is normal with mean mu and variance sigma squared. In this situation, we're going to assume that sigma squared is known because the models that we are going to be working with, we always have one unknown parameter. So we're looking at exponential family of distributions with one parameter, and the other parameter is known. Same thing on assignment number 3 or assignment number 2 in question 3. All right, so we want to derive the score statistic. We can do this in a variety of ways. So in this situation, I'm kind of showing the, or in this situation, what I'm demonstrating would be the traditional method of deriving the score statistic. So we're taking the log likelihood function given the density of a value that's normally distributed. And then we are taking the derivative of that score function. And then we find the expected value in the variance of the score, and we build our sampling distribution for the test statistic or for the for that score function. The other way that we could go about doing this is using the properties of the exponential family. So in lecture set number 2, we wrote out general expressions for the expected value for the score function, for the log likelihood function, for the expected value of the score function. Well, not for the expected value, that's on assignment 2, but we wrote out using exponential family components, the log likelihood and the score. So we could also use those to find the score function and the log likelihood function here. So there's different ways that we can attack this problem is the point that I'm trying to make. And those two procedures should match up. Okay, so we have our PDF, we have our log likelihood value, we have our score function, which is given in the red box. Now what we're doing is finding the form of the sampling distribution for that score function. So in order to do that, we have the score minus its mean over its variance. So the mean of the score function is 0. On assignment number 2, we're going to show that this is true in every situation. So for all exponential family members, this is actually the case. But here we're showing it in this specific case for the normal distribution. Okay, then we have the variance of the score function, which is the information function. So we can show that this is n over sigma squared using the variance operator. So therefore we have our score function over its, or the sampling distribution of the score function is S of theta. Technically this is minus 0. So I probably should make a note of that here. I'm just gonna rewrite this very quickly. So we have, therefore, S of U minus the expected value S of U, okay, divided by the square root of the information function. So this would be the formal definition of the sampling distribution. So the expected value of the score function is 0. So we have the score divided by the square root of n over sigma squared. Okay, so now what we can do is a little bit of manipulation here, right? So we're going to have n y bar minus mu divided by sigma squared, which is divided by n over sigma squared to the negative 1 over 2. Yeah, that makes sense, right? Okay. See if I can get this to work out. So then we have n y bar minus mu over sigma squared times n negative 1 over 2 sigma squared sigma to the negative 1. So this is going to be n 1 over 2 y bar minus mu over sigma, which is y bar minus mu over sigma divided by the square root of n. Okay. Okay, and this probably looks very familiar to you. This is the sampling distribution of y bar. So this is the definition of standard normal random variable. So we know that because the data that we started with is normal, that this thing is going to be distributed normal 0, 1. Right. Okay, any questions? So again, this first exercise, what we did is we found an expression for the score function. And then what we did is we found the asymptotic sampling distribution for the score function. So the sampling distribution for the score function is found by standardizing the score function. So we take the score minus its mean and divide by its variance. The expected value of the score is 0. So that's why that doesn't factor in. And then we divide by the square root of the variance of the score, which is the information function. And then from that point, I'm just simplifying, and you can show that this thing is, you know, the definition of the z-score. And in this particular situation, because the data is normally distributed, this result is actually exact. So since y is normally distributed, y bar is normally distributed, and therefore this thing is exactly normal, mean 0, variance 1. For the other exponential family members, it would be asymptotically normal or approximately normal because due to the regulatory conditions attached to those attached to those distributions. Okay, So let's look at another example. Same idea. Okay, so in this situation, we have a binomial random variable. So y1 through yn is binomial with parameters n and pi. So pi is going to be the parameter of interest. This is the probability of success. N is the number of trials in that case, and we're going to consider this to be known. So what we want to do here is derive the score function and the sampling distribution of said score function. Okay. So we can take a similar approach in this situation. So we have f of y is equal to n choose y pi to the y 1 minus pi to the n minus y. Right? So let's go back and just review some of our earlier work here. So if we go back to lecture set number 2, okay, we have our binomial distribution result shown here. Okay, so we have the following. So, okay, so we have the following results, right? And then what we can do is we want to find the score and the log likelihood function. Okay, so we have our log likelihood function shown here on slide 13 from lecture set 2. And then we have an expression for the score function shown here on slide 14. Okay, so let's just take these two things. And again, what I'm trying to do here is just remind you that there's a few different ways that we can get to the same results. Okay, so that's the purpose of this exercise. So we can do this in the traditional way and compute the log likelihood directly from the density, or we can use our exponential family results. So recall. Okay. I'm just going to move some of the stuff around to give myself room. right. Okay, so we have a binomial random variable. We could just structure the log likelihood in the traditional way. So we just take the sum of the log of the PDF. If we do that, we'll end up with the same result that we're going to end up with taking just by taking the definitions that are shown below. So there's two different ways to accomplish the same goal. Then what we could do is take the derivative of the score function, which is what we did for the normal distribution, or we can just directly plug into our formula for the score statistic. Okay. So let's show, first off, just for completeness sake, L of pi given yn is going to be y times log pi over 1 minus pi plus n log 1 minus pi plus log n choose y. Okay, so then we can show that the score function for pi is going to be y. Now we have to take the derivative of log pi 1 minus pi. Okay, so so b prime pi is going to be d by d pi of b pi. So this is d by d pi of log pi 1 minus pi. So this is going to be d by d pi log pi minus log 1 minus pi. So that should be 1 over pi minus plus 1 over 1 minus pi. I think that's correct, right? D by yeah. Be confident in that. Okay. And this is going to be pi one minus pi plus pi. So 1 over pi 1 minus pi. Okay. So then we should have 1 over pi 1 minus pi plus, oh, and then we need c prime theta. So that's going to be d by d pi of C pi. So that will be minus n over 1 minus pi. Okay, so that's going to be y over pi 1 minus pi minus n pi 1 minus pi. Which is y minus n pi. Nice. Okay, so now we have an expression for the score function. So this would be the first thing we need. And again, the purpose of this illustration, I can't highlight this enough, is that because we understand how the exponential family is structured, and because we have these general definitions of the log likelihood function and the score function from the exponential family, we can get at this result in two different ways. So in the first illustration for the normal distribution, it's like that was the traditional approach: set up the log likelihood, take the derivative of the log likelihood, and work from that. In this second approach, we've already done that work for the general exponential family, and now we're just using those rules to get to the solution that we want. So the score function here is found directly by plugging into our expression for S beta. It's just that now it's S pi because theta is pi. Right. Any questions? Okay, so now all we have to do is standardize our score. So we need to find the expected value of the score function, and we need to find the variance of the score function. And again, the variance of the score function is the information matrix. So we're actually going to show that for any exponential family member, at least the ones in canonical form, but this might be true. I think this would be true regardless, that the expected value of the score function is going to be 0. So we can work this out pretty easily in this case. Like, so if we want to do it specifically, we can do it for this particular problem, but we know that this is always going to be true. Okay, so the expected value of the score function is going to be the expected value of, sorry, I won't skip a step. That would be presumptuous. So it's going to be y pi divided by pi 1 minus pi. Okay, so that's going to be, now I need to simplify. Okay, so we only have one random variable here, so that's going to be the expected value of y minus n pi divided by pi 1 minus pi. Okay, so y is binomially distributed with parameters n and pi. What is the expected value of y? Does anybody remember? Yep, very good. So the expected value of pi is n pi. So you can see immediately how this goes to 0. N pi minus n pi, pi 1 minus pi equals 0. Okay. And again, in the general case, on assignment number 2, this is the very first thing that we're going to show, is that this is true for all of these different distributions in the exponential family. Okay, so then what we need to do is find the variance of s pi. So this is going to be the variance of y minus n pi over pi 1 minus pi. Okay, so this is going to be 1 over pi 1 minus pi. I guess we can write it like this, all squared, multiplied by the variance of y. And then what is the variance of a binomial random variable? Okay, so you were ready for that question. Okay, so that's going to give us n over pi 1 minus pi. Okay, okay, so therefore the score function for pi minus the expected value of the score function for pi divided by the square root of the information function for pi is equal to y minus n pi divided by pi 1 minus pi multiplied by n over pi 1 minus pi to the negative 1 over 2. All right, so we're going to have y minus n pi square root of n divided by the square root pi 1 minus pi. Oh, this is to the okay. And that gives us y minus n pi divided by the square root of n pi 1 minus pi. Okay, and then this thing, because y is binomially distributed, is approximately normally distributed. Okay, so it's no longer exact. Okay, and this would be approximately normally distributed. Oh no. All right, so a couple examples of deriving score functions and their sampling distributions. Any questions? So these illustrations that we had just worked through are meant to be instructive and illustrative illustrations of the process that we would undertake to find the sampling distribution for a particular function. So in this situation, these two illustrative examples were based off the score function. So while this may not be directly relevant to what we're doing in the course, these two examples were meant to, again, give you a step-by-step process as to how we would actually find these sampling distributions. What we're going to do now is take this idea and generalize it so that we can find an expression for the sampling, for the sampling distribution of the maximum likelihood estimates of our model parameters, so the beta. So the idea is we have now seen two illustrations of how to find these sampling distributions. And we know that in each case, we have to find an expression for the statistic, the score statistic. Then we have to find an expression for the expected value, which is 0. And then we have to find an expression for the information function. We want to do the same thing for the parameters of our GLM, so for the beta. The reason, of course, is that if we know the distribution of the betas, then we can conduct inference about those values, right? So we can build confidence intervals and we can construct hypothesis tests. So we're going to look at a derivation of these sampling distributions now. In order to do this, we are going to require a Taylor series expansion about the function of beta, so about the score function for beta in particular, or the log likelihood function for beta rather. Okay. So the Taylor series expansion, if you don't recall, is given on the current slide. So we say for the function f of x at a point t, we have f of x is equal to ft plus x minus t times the derivative of f with respect to t with respect to x at x equals t plus 1 over 2 x minus t squared, etc. We only need the first couple of terms, so I didn't continue this, but the expression basically continues in the same format. I think it's like 1 over 6 next, x minus t to the cube, and then the third derivative, and it just goes on and on and on. Okay, so we can derive approximations using the Taylor series expansion for the parameters beta and the multivariate beta as follows. So to start off, we can say the following. So from the Taylor series expansion about the log likelihood of beta near an estimate, which we'll call beta hat, we have the following. So we have L beta is equal to L of beta hat plus beta minus beta hat multiplied by the derivative of the log likelihood function at beta with respect to beta hat. Okay, so the derivative of the log likelihood function is the score function evaluated at beta hat. So we can write S beta hat. Okay. And then plus 1 over 2 beta minus beta hat squared. And now we have the second derivative of the log likelihood function with respect to beta. So that's the information function, right? Well, the negative information function, okay, evaluated at beta hat. So then here we're going to have minus the information function at beta hat. And then we can say at the multivariate beta, so at the vector beta, we can write L beta is equal to L beta hat plus beta hat minus beta times transpose times S beta hat minus 1/2 beta hat minus beta transpose information function beta hat minus. Oh, sorry, I just made a mistake. Good catch. So again, what we're doing right now is we're kind of following the same process that we used in the last two examples. So in the last two examples, we found the log likelihood, and then we found the score function. Then we found an approximation for the variance of the score function, and then we put all those things together to find the sampling distribution for the statistic. So the next step here is going to be to basically find an expression for the score function of beta, right? So take the derivative of the log likelihood function with respect to beta. We could do that directly, and I think it would be fairly straightforward to show that if we took the derivative, you'd have the score function plus this constant, well, with respect to beta, the derivative of the score here, and then you would have the derivative of the information function. Okay. So I think we could work it out directly, but we can also show that this, we can also find an approximation of the score function using the Taylor series expansion as well, which is what we're going to try here. So we would have maybe I shouldn't start with similarly. It's okay. So similarly, we can find an expression for the score function using a Taylor series expansion. This gives S of beta is equal to S beta hat plus beta minus beta hat times S prime of beta. Okay. And this is going to be S of beta hat plus beta minus beta hat times the information function of beta hat. Okay. And therefore, at multivariate beta, we have S beta is equal to S beta hat minus the information function beta hat multiplied by beta minus beta hat. All right. All right, so now we have our expressions for the score functions. We need to work out expressions for the information function because what we're trying to do here is basically standardize beta hat, because what we want to know is the sampling distribution of that estimate. So the next thing to do, okay, so find expected value S beta it doesn't really matter. Like we can do it in the multivariate case or in the univariate case. It's going to lead to the same result, right? So, okay, I'll be consistent. So we want to find or the expected value of S beta, sorry. And variance S beta or variance S beta. Okay. Okay, good. I have lots of room. Right. So we have our log likelihood. We drove the score. We're just following the same steps from before. We're trying to work out the sampling distribution for our MLE for the model parameters. So now that we have the score function, what we need to do is find an expression for the expected value and the variance. We know that the expected value is going to be equal to 0. but we can show that this is true as follows. So for the expected value of S beta, okay, we have the expected value of okay. So we have the following. By definition, beta hat is a MLE. So it maximizes the likelihood and is the solution to S beta equals 0. Okay, so the first part, we have the expected value of this statement, right? We're going to, this thing is equal to 0. The reason it's equal to 0 is because first off, we have the score function being evaluated at beta hat. Beta hat by definition is the MLE. The MLE is the solution to S of beta equal to 0. So therefore, S of beta hat is equal to 0. Okay. Zero. Okay, so that's the first part. Right, so this thing goes to 0 for this reason. Okay, now the second part is much easier to show why this, it's much easier to show why the second term goes to 0. So we're going to have the expected value of the information function minus beta times beta hat. Okay. Okay. So now we can say this gives the expected value of if we treat I of beta hat as a constant, then we have I beta hat multiplied by the expected value of beta minus beta hat, which is equal to, so if we treat the information function as a constant, then we have this constant multiplied by the expected value of beta minus beta hat. Okay. And this is going to be equal to that information function multiplied by beta minus the expected value of beta prime, of beta hat. Okay. Okay, and then we can say, since the expected value of S beta is equal to 0, no, that's a roundabout argument. Okay, so since the expected value of beta hat is equal to beta, right? So we know that the expected value of the model parameter is the true value itself. So since the expected value of beta hat is equal to beta, then the expected value of S beta is equal to 0. Okay. So then we can say, okay, so again, log likelihood score, expected value of the score is equal to 0. We need a denominator for the expression, right? So we need to find the variance of beta hat. So given that the expected value of the score is equal to 0, as we showed here, we can then say it follows that the variance of beta hat is given by the expected value of beta hat minus beta hat minus beta transpose, which is going to be equal to the information function at beta hat multiplied by the expected value of S beta. S beta hat transpose times the information function which is equal to the inverse of the information function, beta hat. Since I beta hat is equal to the expected value of pretty general statement. So we now have our expression for the score function. Okay. We have the expected value of the score function is 0 as expected. We have an expression for the variance of the score, which is going to be, or we have an expression for the variance of beta hat. Okay, but we have the expected value of beta as well, which is equal to beta. So therefore, okay, so therefore the isentropic sampling distribution for beta hat is given by beta hat minus beta times the information function of beta hat times beta hat minus beta. And this thing is approximately chi-square on p degrees of freedom. Okay, and this thing is called the Wald statistic. Okay. In the one parameter case, we can write beta hat is distributed normal with mean beta and the information function for beta. All right, pretty long proof, but the purpose again was just to show what the sampling distribution of our of beta hat was. Okay, so we wanted to know, we basically want to know like how it is we can go about conducting inference about the model parameters. And the purpose of this proof was to show that the sampling distributions for the maximum likelihood estimators can be found through the expressions for the score function and the log likelihood function around the beta and beta, around multivariate beta and little beta. So we derived our expression for the score function, and then we showed that this expected value went to 0. One thing that's kind of lost in this, and I realized this when I got to the end, was the key, like, so we have the expected value of beta is equal to 0 as expected. So we sort of showed that as a result, but this is actually the key part here, because this is what we're actually going to standardize by, because we are using the expected value of beta in our expression for the sampling distribution. So this part here, I honestly kind of messed it up a little bit, because I showed the result of the expected value equal to 0, but the key is really that this thing is equal to beta, because that's what we're going to standardize by. And then after that, we found the expression for the variance of beta hat, and that's what we divide by in our sampling distribution. Okay. So obviously I'll stop here. We had our announcements at the start of class, so I won't go over those again. We have lab tomorrow. I have office hours tomorrow, and we will just pick up with this on Thursday. And if you guys have any questions, please let me know.